For problem 2, we will have the same wire as in problem 1. The length of the wire is L, the cross-sectional area is A. This wire is connected by ideal wires with zero resistivity to a battery of voltage of given voltage V. The resistivity of this wire is changing according to rho naught, that is constant, X, that is a variable, and divided by L, length of the wire. We want to find how much charge is there between L over 4 and L over 2. This point is length over 4, and this point is L over 2. So what we are looking for amount of charge within this piece of this wire. Well, how to think about this problem? We are given the resistivity. We understand that we can find the electric field. Electric field is rho J according to Ohm's law. If I know the electric field, then I can use Gauss's law to find the amount of charge. Flux through the closed surface of E of the electric field, so E dot ds closed surface, is Q enclosed by this surface over epsilon naught. So if I know the flux out of this cylinder, then I can find the charge. Okay. First of all, we need to find the electric field. How to find the electric field within this wire? We already did it in the first problem, so I will move really fast and we will do it again. So I have E, which is rho J. If I knew J, then I just take rho that is given and multiply it by J, which means that I need to find J. How to find J? Current density. I will find current density by finding first the difference in the electric potential. V at L minus V at 0. If I take absolute value, because I need to find magnitude of J, this is V. Absolute value, I don't care about this minus its magnitude. It's integral now from 0 to L. E dot dr. And then this is equal to integral from 0 to L. Electric field is rho J. Rho is rho naught X over L, and then J dx. J is constant. I take it out of integral. Rho naught, unknown constant. We are looking for J. Rho naught over L, J, and then X squared over 2, upper limit, L squared over 2. L and L squared, I have rho naught J L over 2, which means that J is equal to, let me finish here, J, current density, is equal to 2V divided by rho naught that is given, rho naught L. Now we know J, we know the current density, we know the electric field. The electric field E is rho, which is rho naught X over L, that was given, times rho naught J, and J is 2V divided by rho naught L. So I have rho naught, let's simplify it. We have 2V, I put a vector here, so let's first put magnitude. 2Vx divided by L squared. And if I want it as a vector, we understand that the electric field is rho J, J is to the right. This is direction of J, direction of in the same direction as the current, and then E is 2Vx divided by L squared, and I put here Ix, unit vector in Ix direction to show the direction of the electric field. So electric field is 2Vx over L squared Ix. Now we have our usual problem on Gauss's law. This pink piece of the wire, this is a cylinder, we understand it, right? So this is a cylinder, and we need to find the flux of the electric field out of this cylinder. We found the electric field 2Vx over L squared Ix. It is in positive x direction. Within this wire, the electric field, let me use a different color. It is to the right in this direction. This is the electric field. Now we can use Gauss's law to find Q enclosed. So we need to find the flux of the electric field out of this cylinder. This is a cylinder. We need to find flux out of this cylinder. This is A and this is A. So what is the flux through a curved surface? So let me redraw it. I have this piece of wire. This is L over 2. This is L over 4. The electric field is in this direction. This area is A. This area is A. And I need to find the total flux. So it is flux through the curved surface, and then flux through the left surface, left, and then phi through this right surface, and this is equal to charge enclosed over epsilon naught. Charge enclosed over epsilon naught. Q enclosed. Okay, so what is phi through the curved surface? Area vector for the curved surface in the radial direction, radially out. Electric field is in the x direction, in this x direction, which means that dot product of area vector and the electric field is 0. They are perpendicular to each other. So flux through the curved surface is 0. This is area vector, this is electric field, no flux. Now what is the flux through the left surface? For the left surface, let's first find the magnitude of the electric. I put it in opposite way. So this is, I look from the left. This is L over 4 and this is L over 2. Now it is correct. So what is the flux through the left surface, this left surface? First of all, we need to find the electric field through the left surface. Do we know the electric field? Yes, we use this formula. We know the area vector, so we can find the flux. So phi left, that's what we are writing now. The electric field is to the right. Area vector ds is to the left. Dot product E dot ds is negative. That's why I put minus for phi left. Now the magnitude of the electric field is 2V. X is L over 4. L over 4. Then it is L squared right here. This is the electric field. ds, the area vector, this is A. And we already took into account direction by putting minus here. Then what do we have? This is phi left. We are done. What is phi right? Flux through this surface. Electric field is to the right. Area vector is to the right. I remind you that area vector is out of closed surface. That's why this one is to the left and this one is to the right. This is ds. Do we know the magnitude of the electric field right at this surface? Yes, it's constant because x at each point of this surface is L over 2. Electric field is in the same direction as ds plus, so I have 2V. X is L over 2, and then L squared. What is area vector? Area vector is A. Okay, and this is equal to Q enclosed. Q enclosed over epsilon naught. Let's simplify it a little bit. L squared L cancel out. L squared L, they cancel out. So what will be Q enclosed? Charge enclosed is epsilon naught. And then I have here minus, let me factor out epsilon naught, and then I will factor out 2V over L. And then what I have in parentheses is minus 1 over 4 plus 1 over, oh, I forgot A. We also factor out A right here. And then plus 1 over 2. Minus 1 over 4 plus 1 over 2 is plus 1 over 4. So I have epsilon naught. And then 2 here, VA divided by L. 1 over 4 here, 2, 4. What will be my final answer for the charge enclosed by the surface? It will be epsilon naught VA divided by 2, 4 here, 2 is left, divided by 2L. So this is the charge enclosed by this cylinder, this piece of this wire between L over 2 and L over 4 and L over 2. So we found the charge using Gauss's law.